I've been working on spatiotemporal modeling of network data using some of the kernel methods that Professor Shaw-Taylor mentioned earlier. So just to give an idea, probably more of an idea of the data that we have. This is the AMPR system data. So this is automatic number plate recognition data. So each one of these different colors is a link which has a camera at each end, and travel times are recorded on those links. So if I just zoom into an area of this network here, so we're actually here at the moment. So say I was trying to predict travel times on Gower Street, which is just over there. What kind of information can I use? So first of all, what is often done in traffic is to use temporal information only. So this is quite useful because you have a time series of what's happened there before. You know what's happening there currently, so you can sort of try and forecast what's going to happen. And this tends to work quite well. So using a method called kernel ridge regression, we're able to model quite accurately what happens on links like this. So up here you have a comparison between some of the sort of more traditional linear methods and the kernel ridge regression here. And this is in terms of R². So you actually get quite good results. However, when we use this purely temporal approach, there's certain things we can't do. So we can't predict when there's sudden changes in traffic, because if a car crashes, you don't know that's going to happen. However, and also if there's a lot of missing data, which is the case in this network, sometimes up to even 100%, you don't know what's happening because you've got no local temporal information. However, if you have spatial information and you know what's happened sort of upstream and downstream, then you can get more of an idea of what might happen soon. So we might use the adjacent links on this network to try and forecast travel times on this link. So doing this, we can actually do quite well. So this is another example where we've used just the previous information from the upstream and downstream links to predict what's going to happen on a link. You can see in general the black line, sorry, is probably a bit difficult to see, but the black line is the real data. And then there's three different methods here: kernel ridge regression, a nearest neighbors approach, and a standard historical average there. You can see that this generally does quite well. However, there's certain cases where it will perform less well. So I don't know if you can see that green line. Which was the button for the light? Off, yeah. So sometimes we have a case like this where we're over-predicting, or possibly under-predicting, but it's easy to see the over-predicting here, something on this link. And this happens because something happened upstream or downstream that didn't have a spatiotemporal effect. So basically what we're saying is sometimes these phenomena can spread, and sometimes they don't. So if we look at this network, it's quite easy to see why this might be the case. This is quite a sparse network, and you can see there's many other roads. So just to give some examples, from my knowledge of this area, I know there's a road that flows in here, another one here, and Torrington Place there. There's a lot of traffic entering and exiting this link. So it makes it more complicated. You can't use a sort of physics-based model that you would use in a highway where you would say traffic comes in this end of a link and leaves the other end, so you know exactly what's going to happen. So the thing to do next is to use other forms of adjacency. Now this is sort of future work, but there's an underlying network here, which is the ITN network, which you can get from Ordnance Survey. So we can actually build the adjacencies between these links. So you might now find that Tottenham Court Road here is actually related to Gower Street here, even though in our network representation it's not. And then moving on further from that, there's plenty of other information that's being collected all the time in London. So for instance, the TfL has incident data sets. So you might know that there's roadworks here, or you might know that there's been a car crash here at some point. So you can bring in this kind of information in a sort of data fusion way to enhance your predictions. And that sort of lends itself to the kernel approaches that Professor Shaw-Taylor was talking earlier, where you can bring in these different data sources and combine them. And even in the future, possibly we'll be able to even use social media data. So if somebody's sitting in a traffic jam and they're on their smartphone because they're not moving, and that's sort of a legitimate thing to do, they might suddenly write hashtag traffic jam. And you might have a collection of those sorts of things in one location. So I should probably turn the light back on. Yeah, and you can sort of, maybe not, you can combine those sorts of information in to provide better predictions. And yeah, well, that's pretty much it for me. Let's just give you a flavour of the sort of things we're trying to do. Okay, thank you.
Very good.